And that was just pure trauma. All right, I think, yeah, so, let's see. Camila, we have like that homework assignment due on Wednesday. Did you have any questions on it or anything? Okay. Cool.
It's hard, but I'll try to figure it out.
What's that?
It's hard, but I'll try to figure it out.
It is hard, but we can talk about it if you want. But don't let me force anybody to do anything. All right, let me find the, where we're getting rolling here today. Oh shit, that's really old. I won't give you a new assignment until Wednesday, for sure. Sorry, it's taking a while. There we go. Okay. So, we're gonna spend some time talking about infinite series. Not super deep, so some of this stuff will be like, I've never seen a proof of anything for infinite series, because I don't know who you took Calc 2 from, but I don't generally prove a lot in Calc 2. And by the time we get to series in Calc 2, it's the end of the semester and I'm desperately trying to get just shit done anyway. But let's just talk about a few infinite series here. Let's do that. This is kind of a nice warm-up because I feel like you're probably kind of on top of this stuff. Any recollection of the name of this infinite series? It's got a special name. If you play a musical instrument with strings, the name might... Oh, sorry, yeah, you're just like... Divide the string in half, divide the string in thirds, perfect quarters. What do you call those? What do you call those?
A harmonic?
The harmonics. It's the harmonic series. Now, we're going to talk more about what convergence and divergence means for these, but do you remember if this converges or diverges? In other words, adds up to a finite sum. If we got out Excel and started adding this up and keeping it cumulative, would it settle down? Saying yes?
I would guess, yeah, because like as the fractions get smaller, kind of like.
Let's get a count here. 1, how many say it converges? 2, 3. Is that a yes? What do you think, Camila? Think so? Wow, we got 5. All right. Damn, unanimous. I'm not going to put my vote up. Okay, so let's see, what else we got? We got 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, blip, blip, blop. Kind of the same, definitely different. Notice the denominators are a lot larger here, so these are smaller fractions, everything except the first one. So yeah, this is 1 plus a quarter plus a ninth plus a 16th and so on down the line. And then I wanted to do one more, which was, let's see, what was this? I was feeling very clever about this. Yeah, so 1 over 2 to the first, 1 over 2 squared, 1 over 2 cubed, 1 over 2 to the fourth, blah, blah, blah. So kind of all these last two slight permutations. There's a similarity in all of these. They're also very different. Do you recognize any series? So like, well, tell me some terms. I just want to see where we're at. Like, tell me some words you remember about series. You don't even have to define them. Just like, tell me kinds of series. Wow.
I was gonna say algebraic, but I don't think that.
I don't think so either, but I like it. There should be. That's a cool idea. So we got harmonic series. This is actually a special type of one kind of series.
I remember the Taylor series, maybe?
That's much fancier. So that is an infinite series. It's when we expand a function into an infinite series. So that's like a Taylor series. Definitely an infinite series. You recognize it? What about this one? This is a very special one. This is where we're going to start today. That's cool. That's all right. We just had a break. We're coming back. This is actually one thing you could notice here is that to get from term to term. So first off, this is a series. The things that I'm adding, these are the terms of the series, the components that we're adding together. Those are the terms. And notice here that to get from the first term to the second term, I multiply by a half. From the second term to the third term, I also multiply by a half. And then that just keep on going. So here, subsequent terms I get by multiplying by a half. These two are not like that at all. There's no constant multiple between these two terms, these two terms, these two terms. Does that help you remember maybe what kind of series it is?
Is it geometric?
Oh, hell yes! Yeah, you made that frown because you were worried, but yes, that's solid. So this is a geometric series. Yeah. Good job, Liv. Thank you. Geometric series. I kind of want to start there because one of the big questions we want to answer, and we want to understand this more deeply than we have when we took Calc 2, is does this make sense? Does this weird infinite expression even make sense? And to make sense, we're going to say is to converge to a finite value, to settle down to a finite value. But we're going to make this all very solid. Let's start with this guy here. So let's just do a whole bit on geometric series, and the more you see this, the deeper this will get, and one day you'll be able to just derive this shit from scratch. I have my best and oldest friend made his fortune in business by knowing about infinite geometric series. You don't have to know a lot in business to like impress people, especially math. So like you could all go to business and then be like, oh, I know this, and they'll be like, oh my God, I hate math. And they're in business because they didn't know what else to do, probably. That's what it seems like a lot to me. I've had a few business majors who were amazing at math, but overall, they did not want to be in math. So with some math and some business, you could pretty much rule, like, this guy's like, he's a multi-millionaire now, he's so freaking rich. It's good to be the friend of a rich guy, because all his garbage is awesome. So he's always throwing stuff away and like, hey, do you want to come look? I'm going to throw some stuff away. And I'm like, fuck yeah. It's always just top-notch crap. Anyway, here's part of how he made his mark in business, knowing geometric series. So let's start off with a finite geometric series. Finite geometric series. So I'm going to call that S sub n. It's a sum with n terms, and they're going to roll like this. First I start with a constant, and then kind of following through with this rhythm where I'm multiplied by the same number to get to the next thing I'm going to add. I'm going to multiply by r and get that next term. And then I'm going to multiply by r again. Same r. That's the key here. A common ratio. common ratio between terms. And then we keep going. And what should be, if I want this to have n terms, what should be my final exponent? N minus 1. Because when I had 2 terms, the power was 1. When I had 3 terms, the power was 2. So I expect this to be n minus 1. Cool. So our first goal is to figure out a closed form formula. Closed form formula for this sum. Another good thing as a math person to just have this. Honestly, these are probably the most prolific, the widest seen kinds of series in the world. So knowing something about geometric series gets you very far. So what I'm going to do is multiply both sides of this by that common ratio r. So I multiply by r. And I'm actually going to be careful here. I'm going to shift some things. So notice a times r is that term there. So that a times r gets me that. This is ar squared. Keep doing that all the way down. Eventually I'll get to ar n minus 1, because right in front of that, there's this guy. And then that times r gets me that. And then finally, my last term is ar to the nth. That's this guy times that common ratio r. Is this all looking good? Now I'm going to subtract. So this left side, I've got s sub n minus rs sub n equals, I'm liking my s's today. Feeling pretty happy about the way those look. A minus 0 is just a. Everything else cancels. Except for that final term, and I'm subtracting. So I get that. How we feel? Let me know. This, I could do a little factoring, right? That's actually 1 minus r times s sub n. And over here, I could do a little factoring, like that. Pretty. And then I'm going to divide by 1 minus r. So this implies that s sub n equals a times 1 minus r to the n over 1 minus r. There's our formula. That's a pretty sweet formula, kind of amazing that we could turn this sum, no matter how big it is, into that closed form. But here we go. Let's actually make some notes here, because this isn't how you'd want to remember this. So if we were doing our heuristic, just like a way to help us memorize this, notice that a is the first term. This is the first term in the series times 1 minus the common ratio to the number of terms in the series divided by 1 minus the common ratio. So we can come back to this guy. Add it up. This is actually Zeno's paradox. What's Zeno's paradox? If you've been in one of my classes, I don't know how you haven't heard this, but maybe it was just the wrong class. What's Zeno's paradox? Greek philosopher, thought a lot about motion. Do you remember how this rolls? Goes a little like this. If I want want to travel the length of this board. So this was a logical argument that Zeno made. I first have to travel half the distance. To get to the end, I still have to travel half that distance. Still have to travel half that distance. And you see the problem here is I just keep traveling half distances, never closing in on that final. There's always another half that I could go. In our minds. In reality, maybe that's not so great, not so possible, but that was Zeno's paradox. So look here, we've got 1/2 plus quarter, so this is that first step, plus half the next step, or half the next distance, plus half that next distance. And what we want to do is add that up. Step one is I recognize that this is geometric. It's geometric because to get from one term to the next, I multiply by the same number. So it's geometric with r as a half. We kind of need to push one more thing here first. Let's truncate this because I can't quite get to the infinite case yet. We got one more thing to do. Let's make this 2 to the 10th here. And I don't know what 2 to the 10th is. 1024? Can somebody check that out for me? Were you doing it in your head? I heard you like.
Oh, it was in 2 to the 8th, 60.
2 to the 6th is 64. 2 to the, so let's just do it. 2 to the 7th is 128. 2 to the 8th is 256. That was where I was starting. And then 2 to the 9th is 512. 2. All right, I think I got it. 1024. So this series right here, I can add up just using that formula. Definitely geometric. How many terms are there? 10. You can look at them. The terms are indexed by the exponents, right? 1, 2, 3, on up to 10. So there's 10 terms. So using this formula, the sum of the 10 things is going to be the first term times 1 minus the common ratio to the nth power, which is the number of terms, over 1 minus the common ratio. The bottom is going to be a half. That's going to cancel with this half right here. So notice this is just this. This is 1 minus 1024. And that would be 1023 over 1024. See if that's looking okay. Feeling good about that, Camilla? All right, let's take this formula now for a finite geometric sum and push things to infinity. So I'm going to take this formula here and think about what happens when I just let this thing rip and go all the way out to infinity. There's a lot of stuff that we haven't, that doesn't encompass when the thing goes out to infinity. So now we're going to let n go to infinity. So i.e., I don't know why I capitalized that, i.e., explore the infinite sum, which looks like this: a plus ar plus ar squared plus ar cubed, dip, 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 on out. And the way to do that is with our nice formula and the finite sum. Recall that S of n equals a plus ar plus ar to the n minus 1. And that is equal to this. That is equal to a times 1 minus r to the n over 1 minus r. We derive it. So I'm going to let n go to infinity on this left side, and that'll turn it into the infinite sum. On the right side, notice there's only one part that moves with n, and it's that r to the n. So let's do a little bit of side work here. Got a fixed number raised to the nth power. We're going to get some different answers. What happens if r is 1? What if r is fixed at 1? What does that do? Stays constant at 1 because it's 1 to the nth power. What if r is equal to 2? What happens? Goes to infinity because 2 times 2 times 2 keeps blowing up. What if r is negative 2? What does it do? Can you picture this in your head? If r is negative 2, oscillates getting crazier and crazier, right? First it's negative 2, then positive 4, then negative 8, then positive 16. So you get that oscillating. We're going to say that we're going to break it down into some cases. So this equals 1 if r equals 1. This sequence, this is a sequence, right? We have 1, r squared, r cubed, r to the 4th. We're thinking of that as a sequence, which is going to be a common theme for how we think about series in general. This sequence diverges if r is less than negative 1, less than or equal to negative 1, or r is bigger than 1. So this here, this would be like the tightest case is r equals negative 1, and then you're just oscillating back and forth, you never settle. If r is negative 2, like we talked about, it blows up, but it's oscillating. And then out here, this is just straight blows up. It goes to infinity, like Cormick says. A nice way to say this would be this. Well, let's actually just leave it like that. What if r is a number between -1 and 1? Then what happens? What's that? It goes to 0. It's a fraction. Right, so let's take a look here. So for example, if r was a half, then the sequence is a half, a quarter, an eighth, a 16th, and we can see that that's headed to 0 pretty easily. If r is negative a half, kind of the same thing, except it heads to 0, but it oscillates its way there. I said oscillates really weird. Still goes to 0, but it's rocking like that. So here we're going to put 0 if the magnitude of r is strictly less than 1. Now check out this formula. What are some bad values for r here? 1. We definitely don't want r to equal 1 if we want to use this formula. So this is going to be one of our Verboten cases. And this thing would settle down in these cases here. So this is the only thing we're going to be interested in. So if the magnitude of r is less than 1, in other words, it's between, let's just write that out just so we can see it. If that's the case, then as n goes to infinity, this left side becomes an infinite series. So this is an infinite geometric series. And this right side, what happens to the right side as n goes to infinity? in this case here? You get a number. What number is that? Yeah, beautiful. So this goes to 0. You just got a times 1 over 1 minus r. That is really, really quite beautiful. That is if magnitude of r is less than 1. That's the only time we can add up an infinite geometric series. So now we can come back over here and get our sum. So let's add some ellipses, a plus and some ellipses here. An ellipse says something, I don't know how singular or plural that is. So here, step 1 is I realize geometric. Oh, I was like falling asleep on the way in today, like just driving. I was like at the stoplight and I just closed, I was like, oh shit, I'm gonna fall asleep at the stoplight. It's geometric with r as a half. Since r is less than 1, it converges. So I just make all those little notes. And it converges to first term. So notice what this formula is again. Let's write it in a mnemonic way. This is first term over 1 minus the common ratio. Great way to remember it. So here my first term is a half over 1 minus the common ratio of a half. It's a half over a half. It's 1. So you do make it across the board given infinite amounts of time. This didn't all happen until much, much later. I'm not quite sure what the history of geometric series is. I guess I want to say like the 1800s. I was going to start going into the philosophy of this. Let's just leave it be. Let's leave it be. But let me give you one. Let me ask you this. What would happen? So if, let's say I got confused about Zeno's experiment, and I want you to help me out here. And instead of doing the half of what's left, half of what's left, what I did was I stepped 2/3 of the way across, and then 2/3 of the way back, and then 2/3 of the way forward that's left, and then 2/3 of the way back, and then 2/3 of the way forward. So in other words, what is this sum? So let's think about how that went. I went 2/3, and then I went back 2/3 of that. And then I went forward 2/3 of the remaining, of the distance I just traveled. First off, how do we know it's a geometric series and what's the common ratio? What do you think, Camila? What do you multiply to get from here to here? Negative 2/3. Yeah, so that ratio can be negative. And when you see it alternate like this, that's what's going on. Does everybody see that? Negative 2/3, negative 2/3. The next term would be negative 2/3 to the 4th. Keep on rolling. So Camila helped us out with that. And since this is less than 1, I can use the infinite formula. Converges. And it converges to first term over 1 minus the common ratio. Be super careful, use parentheses, because it's actually minus minus. And then what does that turn out to be? How far did I end up going? don't get a calculator out or anything like that. Keep a fraction life. Five-thirds in the bottom. So 2/5. So I only end up going 40% of the way. Even though I moved the 2/3. I always thought, I don't know, for some reason I kind of like that. I think it's just kind of surprising and cool. Okay, that's kind of all I wanted to say about those guys, but I do want to move on to some other fundamental series. So we can get a dictionary, kind of a toolbox, and then we can start analyzing series. And I'm probably gonna give you more challenging ones in here than you would have got in Calc 2. Did any of you have Calc 2 with me? I feel like Liv, you did. Yeah. That's it. Okay, next series kind is P series. So there's really two kinds of series we're going to understand in our lives: geometric and P series. The book doesn't really give a proof about this, but I'm going to do it to kind of call back some Calc 2 ideas for us. So P series looks like this: sum n equals 1 to infinity, 1 over n to the p. Sorry. I cut the tip of my finger off over break. Yeah, and I just jammed it into the boards. Not a good thing. So take a look at the geometric compared to the P series. They're kind of flip sides. Here the exponent moves. Exponent moves. The base is constant. The base is constant, equal to our common ratio. Here, the base moves, the exponent is fixed. So here the base moves, exponent is fixed. And if I write this thing out, it's 1 over 1 to the p, 1 over 2 to the p, and on down the line. This is a problem. See, I had like a beer. I never drink, and I was like, it's break. I'm gonna drink a beer. Gonna drink a beer and cook dinner. Well, I cut my fucking finger off because I just can't like even drink a beer anymore. There was a time when I would not have cut my finger off. It would have taken many more beers. Okay, it's a better life where I'm at now. All right, so when does this thing converge? What I want to do is look at a slightly different problem, but very related. Let's take a look at the function f of x equals 1 over x to the p. And think about that for integer values of x. So here's x, here's 1 over x to the p. So when I have 1, my output is just 1. But I could think of that as 1 over 1 to the pth power. Then when x is 2, I've got 1 over 2 to the p. When n is 3, I've got 1 over 3 to the p, and so on. And those are headed down, provided p is positive. So here I'm kind of working on the assumption that p is positive. Does that picture make sense? If I drew out the whole function, it would look like this. But but we're just sampling the function at these very unique points. And what I kind of want to do is figure out what is the sum of that height plus that height plus that height. So there's a little trick. We're going to think about integrating this. In fact, I'm going to think about the integral from 1 to infinity of 1 over x to the p dx. Now, how does that, what we have to do is figure out how does that relate to our series that we're interested in. So notice that our series is actually the area of these rectangles here. So look, the area of this rectangle, base times height. Area is 1 over 1 to the p. Area of this one's 1 over 2 to the p, 1 over 3 to the p, and so on. How do those areas compare? Maybe we should start. Yeah, so how do the sum of these areas compare to that integral? And there's one little trick here that, like, this integral is kind of this area here.
So would like the integral be greater then? It's got like this.
It does, yes, definitely. I just have to kind of finagle this first bit here. So what we could say is that this, how about we do it from n equals 2 to infinity of 1 over n to the p. And I want to put this piece in because the area of that integral is this. What happens if I do this? What's the problem with that? Yeah, we've got this singularity right here, right? We've got this asymptote, and that's going to screw things up. So I want to keep that integral from blowing up in the integrand. I want to keep it only one kind of improper, and that's with the infinity at one limit. So notice that if this is finite, if this thing is finite, adding on this first term doesn't change that. Does that make sense? So let me write up what I'm saying. So note that this sum, n equals 2 to infinity, 1 over n to the p, is finite if and only if this sum is finite. Just because this only differs by 1, this is literally 1 more than this one here. So this is equal to this. I don't want it to look like a 0, plus 1. So if this thing's infinite, this thing will definitely be infinite. If this thing's infinite, this definitely will also have to be infinite. So now I come over here and I see that if I integrate from 1 to infinity, I'm going to get this area here, and that's going to give me this bound on this piece of the series. So let's do this integral here. This first has to be converted into this. Boy, Liv, that's like another lifetime ago that we had Calc 2 together. That feels like a million years ago.
It was like over 2 years ago.
Oh my God, crazy. All right, so I want to do this thing here. Now, I've got to worry about some special cases. First off, we assume P is positive. But there is one special case that I want to take a look at here. So if P equals 1, this integral looks like this. And the reason I broke that out is because the antiderivative of this is a little different than if you actually have a power there. What is the antiderivative of 1 over x?
It's like -1 over.
Can't use the power rule. You can't, because when you do the power rule, if you boost that up by 1, it goes to x to the 0, and then you have to divide by it. So you can't use the power rule, but I like that you're thinking power rule.
Just natural log.
It's natural log. That's it. It's the one weird one. So this is equal to limit as b goes to infinity, natural log of x from 1 to b. That is limit as b goes to infinity, natural log of b minus the natural log of 1, which is 0. And what is that limit there? What happens to natural log as you move out to the right? What's the graph look like? What's limit of b as b goes to infinity for natural log? Infinity. Natural log looks like this. Keeps growing, grows slow. In fact, the rate of growth approaches 0 as we head out that way, but this goes to infinity. So that doesn't actually give me a lower bound here, but so anyway, that's a troublesome spot because this is actually equal to infinity when p equals 1. So all that's saying is that this sum is less than infinity. What I'm trying to do is actually get a better sense of when is this thing finite? So let's take a look at some other values here. Let's assume p is bigger than 1. We know p equals 1 is no good. So assume p is bigger than 1. And now I've got, again, this integral, limit as b goes to infinity. And I'm going to put this back as x to the negative p dx. P is a number bigger than 1. So let's actually assume this might actually help. P equals 1 plus epsilon, where epsilon's a positive number. It'll actually help in the computation. So again, I'm assuming the p is bigger than 1, so it'll help to just do this. And you'll see why in just a second. So in other words, this is limit as b goes to infinity, integral 1 to b, x to the negative 1 minus epsilon dx. Could you do me a favor and work that through? Now, Christian, now your power rule. And you'll see why I rewrote it, I think. I'm gonna run to the restroom. I'll be right back.
all that. Wait. So P. So I think you miscopied something a little bit. I'm saying P is one, so that's actually a 1 right there, which makes life. You see how nice?
You see, yeah. Righteous. Of course, I'm going to ask somebody to tell me what the limit is. Person might be Cormick. How do you feel about that limit?
Better.
Do you feel good enough to give an answer for that limit?
I think it's 1 over epsilon.
I think you're right. So let me slow down here a little bit. Is there anything I can clear up getting to here? So look what I did. I replaced P with 1 plus epsilon. So this becomes -1 minus epsilon. And I did that so that when I did the power rule and added 1 to the exponent, that would cancel with that -1 there. So when I add 1 to the exponent, I get a new exponent, divide by the new exponent, and notice that you just get, I kind of skipped a step here. You just get x to the negative epsilon over negative epsilon. And that made life a lot better. Then I plugged in the b, I plugged in the 1, rewrote 1 over minus epsilon is -1 over epsilon out front. That's just a constant. I'll pull that out front, and if I rewrite this one more way, I think we can all see what how Cormick got his answer. So this is 1 over b to the epsilon, and that's why epsilon's a positive number. So writing it like this is not deceiving us in any way. That limit goes to 0. So I've got -1 over epsilon times -1 over epsilon times -1, good old +1 over epsilon. So let me slow down a second, make sure we're good. I want to make sure Mr. Christian is feeling okay about this. Yeah? Cool. So check out this integral. Just like think about what we've got here. As epsilon gets smaller, what happens to the value of the integral? So as p gets closer to 1 from the positive side, like 1.01, 1.001, what happens to the value of this integral as epsilon gets smaller? What if p was 1.0001? What's the value of this integral? over the epsilon, right? Yeah, so this is equal to 1 plus 0.00001. This is my epsilon. It's how much I'm tweaking above 1. And we've got a formula for it. So the value of this integral is equal to 1 over, as Cormac said, this beastly thing. And that is actually a 1 with 5 zeros behind it. 1 over 100,000, something like that. Is that right? Yeah, let's see, because that's dividing by 100, hundredth, and that would be 100. So, yeah, I think I got that right. So what happens as epsilon keeps getting smaller? Integral goes up in value. But it's finite, it's always finite. So what this is saying is that this integral here will be finite if p is bigger than 1. And that means this sum will be finite. And one thing I just kind of want to notice here, or you to notice here, is that that bound could go the other way. So take a look, what if I had done my rectangles like this? What if I had made my rectangles like this? Notice that the area of these rectangles is still that sum. 1 over 1, 1 over 2 to the p, 1 over 3 to the p. But now I see that the integral from 1 to infinity of 1 over x to the p is actually less than the sum. And now I'm going to include the whole thing. So when this is infinite, this is infinite. So think about what this is saying here, and this is actually the integral test, that if this integral is infinite, the sum is infinite. If this integral is finite, the sum is finite. So from that, we can come over here, and if you did this whole argument with a negative p, p is like a fraction. I kind of don't want to spend much more time on it. But you can use this same argument to conclude the following. Similarly, if p equals 1 minus epsilon, and epsilon is a small positive number, the integral diverges. Might be worth, if you're ever like looking for some math to kind of just check out and fill in the holes in your education, that would be a good problem to take a look at and convince yourself of that. But we have this, so 1 over n to the p converges if p is bigger than 1, otherwise it diverges. Yes, sir.
If you have p greater than 1, can you say that it converges to 1 over p minus 1?
The integral itself would, but that's a great question. Yeah, unfortunately, it's just an approximation of it, but yeah. This is actually, we don't know many of these. We know, let's take a look at this one again. This one that everybody in the class said converges. Harmonic series. Is a p series with what? P equals what? What does p equal there? P series looks like this. What's p here? 1. It only converges if p is bigger than 1. This series diverges. Diverges because it's p series and p is less than or equal to 1. P P has to be bigger than 1. Can't be 1.00001, but it's still gotta be bigger than 1. So here we have P equals 1. And then we had this one. 1 over 1 squared plus 1 over 2 squared, 1 over 3 squared. I think we had that one. 4 squared. I think I wrote that one up. Does this converge or diverge? Converges. What's P? Yeah, well, right, I guess I wrote it up here, but yeah, it converges. This is one of the few that we actually do know the true sum of, and it's a good one to know for just weird moments in math life. It converges to pi squared over 6. The proof of that's beyond what we'll do in this class, but it's kind of cool fact to know. All right. So let's see. I gotta look at my notes to see what's coming next. I think we just have to do a few tests here. So the geometric and the P series, these are our reference series because we totally understand them. We're gonna get weird series, you're gonna get weird series. And what you have to do is figure out which of these two it's most like and compare it to it. And when I say compare it to it, we've got some tools and tests that we wanna talk about. So let's get those up here. First one is, let's see, I kind of want to just get these up. I might do some of these proofs on Wednesday, but I want to get these convergence, divergence tests up here. So the first one is what's called the nth term test. Yeah, and I'll prove a few of these things when we get back in on Wednesday. But the nth term test is also sometimes called the divergence test. And it essentially says this: if, so all these are referring to a general series, n equals some starting point to infinity. So everything I'm referring to is looking like this. If the terms do not die out, the terms a sub n, the things that I'm adding on, do not diminish in size, then the series diverges. And I'll give you an example, but I kind of want, what's the contrapositive of that? Because we're practicing contrapositive this semester. Christian, you feel like you know that?
If sum of a sub n converges, then a sub n goes to 0?
Yeah, perfect. So the contrapositive is if the series converges, then the terms must die out. Kind of makes sense, right? You're gonna keep adding on stuff for forever and ever. The stuff better diminish in size. Now, the way I presented, I thought I was gonna present this was prove this, and then give you that and say, what's the contrapositive? But we'll practice it anyway. So for example, if I have a series that looks like this, That series. Converge or diverge? Converge. So tell me your reasoning.
Well, just looking at that, like every other one is gonna like cancel out the term before it, so it would just end up going to zero.
Let's check this out. Blah, blah, right? So let me regroup this. Looks the same?
Yeah.
So 0 plus 0 plus 0. What does that seem like that would add up to?
Probably zero.
Probably 0. But what if I actually held off on that first term and then shifted over and wrote this as 1 plus negative 1 plus 1 plus negative 1 plus 1 plus negative 1 plus 1. Now what do I get? 1 plus. So I didn't get the same answer, right? Seems like something might be a little foul with this series. You would hope that these basic rules, the associative property, still holds for your infinite sums. What is a sub n here? What's that? Negative 1 to the n. And what happens to that sequence? So now look, I'm thinking of this as a sequence. Does that converge? If it does not converge, the series diverges. If it does not converge to 0, so notice there's two things in here. A sub n converges and, or does not converge. Converge, or a sub n does not converge to 0. Let's take a look at another example. So this series diverges by the nth term test, or the divergence test. Let's look at one more here. What about this one? What's that series do? That might be, honestly, this might be a little evil. Take this off, sorry. That's, sorry. So it's 1/2 plus 2 plus 3/4 plus 5. What do you think of that? So what's your reasoning? Are they? What's the limit of that? N over n plus 1? see what I'm saying?
Yeah.
So where are we headed? Think. Where's that going? As n goes to infinity. Approaching one, right? So this approaches one. So eventually, and you can kind of look here, eventually you're gonna have stuff like this. 1 million, like I was talking to Miss Camilla about, over 1,000,001. You put that in your calculator, it's almost 1.999 something. Notice here that the top is going to infinity, the bottom's going to infinity. So what are some ways we could do that limit? Give me one way I can find that limit when I have infinity over infinity. Also 0 over 0. What's a calc strategy? L'Hopital's rule. I could L'Hopital that. So I could L'Hopital that. Derivative of the top with respect to n is 1. Derivative of the bottom with respect to n is 1. I just literally get 1 right out of that. So L'Hopital's takes me right there. I could do an algebraic approach. Divide the top and bottom by n. Notice I just multiply by 1 over n in the top and the bottom. This makes it a lot more obvious because this goes to 0. And I just get 1 over 1. So however we see it, we see that these terms are approaching 1. So a sub n is approaching 1. So by the divergence test, the nth term test, I'm going to say it multiple ways because it's definitely said multiple ways. The series diverges. Let me give you a few more. Let's kind of stick with what we know. The only thing you know right now is that a p-series with p bigger than 1 converges. And you also know a geometric series converges when the common ratio is less than 1 in magnitude. Those are the only two things you know. This is purely a test for divergence. It can't give you convergence. So just be super careful with that. So let's try another one here. What about sum n equals 1 to infinity of -2 over the square root of n? I'm going to give you a couple. Sum n equals 1 over infinity of -2 over 2 to the n. This is -2. I don't like that. Let's make it -3. Make this -3 too. I want them to kind of look the same, but not really the same. So my question to you is, do these converge? Do these diverge? Knowing what you know right now. check these out. Check yourself. This one here, is actually -3 times something that I can recognize if I just rewrite with exponents. P series, P equals 1/2. Since that is less than 1, it diverges. That exponent's gotta be bigger than 1. So this diverges. Over here, this one is a geometric series. Notice that the exponent is moving, the base is constant. Here the base moves, the exponent was constant. So I see this as a geometric series with the common ratio is 1/2. And it might help you to write out some terms here, right? The first one is 3/2. The next one is -3/4, -3/8. And it can definitely help to write those out, to see that common ratio. And once you know a geometric series converges, you can find to what does it converge. So here first I would write, since r is less than 1, it's converges. And it converges to, remember the formula, first term, whatever that is, that's this, over 1 minus that common ratio. So this is equal to -3/2 over 1 minus 1/2. And so that's -3/2 over 1/2, and that's this -3. Sorry I don't have more stuff for you to work on, Christian, since you turned in your homework.
Okay.
Oh, you're okay? You're all right. So that's it for today, my friends. Let's just call it. We'll pick up more of this on Wednesday, and I'll pick up your homework on Wednesday.